Black holes swallow things. Light goes in and never comes out. Matter goes in and never comes out. Information goes in and, after 50 years of argument, probably never comes out either. You already know all of this. But there is something most people do not know. Buried inside the equations of general relativity, there is another solution. A time-reversed black hole. A singularity that only expels things and lets nothing in. It is called a white hole. A white hole is not a science fiction invention. It is not a metaphor. It lives right there inside the equations of general relativity, sharing the exact same mathematics as a black hole. The only difference is that the arrow of time runs in the opposite direction. Black hole, things can only go in, never out. White hole, things can only come out, never go in. Mathematically, both solutions are equally valid. So does a white hole actually exist in reality? Nobody knows. But over the past few decades, some theoretical physicists have been giving increasingly serious answers, and some of those answers are more unsettling than simply saying white holes do not exist. How did white holes emerge from the equations in the first place? In 1916, Karl Schwarzschild was sitting in a World War I trench and hand-calculated the first exact solution to Einstein's general relativity field equations, what became known as the Schwarzschild solution. It describes the curvature of spacetime around a spherical mass. Inside the solution there is a special radius, the Schwarzschild radius. Within that radius, escape velocity exceeds the speed of light and even light itself cannot escape. That is the black hole event horizon. But the Schwarzschild solution itself never specifies which direction time flows. In the 1960s, physicists Kruskal and Zuckeries independently worked out the maximal extension of the Schwarzschild solution, the Kruskal coordinate system. When you unfold the complete Schwarzschild spacetime, what you find is surprising. It does not just contain one black hole region. It also contains a parallel universe and a region that is perfectly symmetric to the black hole but with the time direction reversed. That time-reversed region is the white hole. In the complete spacetime diagram, the black hole is a region you can enter but never leave. The white hole is a region you can only exit from, never enter. The two are connected by an Einstein-Rosen bridge, a wormhole. Mathematically, it is beautiful. Physically, this structure almost certainly does not correspond to anything that actually exists. The two ends of the Einstein-Rosen bridge cannot be crossed by any signal, and the wormhole collapses the moment you enter it. This white hole exists mathematically but cannot be used physically. That said, this is not the end of the white hole story, it is the beginning. Classical physics first sentenced white holes to death. Then quantum gravity pulled them back out. Classical general relativity's verdict on white holes, unstable, cannot survive. The first reason is the second law of thermodynamics. A black hole swallows matter, mixes it, heats it, and eventually radiates it out through Hawking radiation in the most disordered way possible. Entropy increases throughout the entire process and time can only move forward. A white hole is this process in reverse, taking the most disordered radiation and reassembling it into ordered matter to expel. This requires entropy to spontaneously decrease. Statistical physics does not absolutely forbid this, but the probability is so vanishingly small it is functionally impossible. The second reason is more direct. The white hole boundary only allows things to exit, never to enter, but the moment anything at all approaches it, even a stray photon from the cosmic microwave background, that matter accumulates outside the boundary. Accumulated matter has gravity. That gravity perturbs the white hole and eventually crushes it, collapsing it into a black hole or making it disappear entirely. The universe is filled with radiation everywhere. From the moment a white hole appears, it is being bombarded. Classical physics concludes, mathematically valid, physically unsustainable. In 2014, physicists Carlo Rovelli and Francesca Vedato published a paper that set off considerable discussion across the field. Their idea was this: black holes do not swallow things forever. When a black hole has evaporated through Hawking radiation down to near the Planck mass, quantum gravity effects take over. The collapsing matter inside undergoes a quantum bounce, it rebounds and begins expanding outward. The black hole transforms into a white hole. The death of a black hole is not disappearance. It becomes its own opposite. From the outside, the timescale for this transformation is terrifying in its length. Depending on the black hole's initial mass, an external observer might wait more than 10 to the 67th power years. The universe is currently only 13.8 billion years old, and the gap between these numbers is too large to meaningfully compare. But inside the black hole, time flows at an extremely different rate from outside. Gravitational time dilation means a process that appears brief on the inside can correspond to countless universe lifetimes on the outside. The bounce may not feel slow from the inside at all. This model has several things worth paying attention to. The information paradox is partially resolved. If the black hole eventually becomes a white hole, the information that fell in will emerge from the white hole in some form. It was never truly destroyed, only compressed and delayed by an unimaginable length of time. There is also a specific observable prediction. If primordial black holes formed in the early universe with masses between 10 to the 12th and 10 to the 14th kilograms, they should currently be in the quantum bounce phase, producing gamma-ray bursts with a characteristic timescale of around 10 to the -4 seconds and energies between 10 and 100 MeV. That is a real number a telescope can test. The most troubling possibility, is the Big Bang a white hole? The definition of a white hole is a singularity that expels matter outward and lets nothing in. The description of the Big Bang is that the universe began expanding from a singularity of infinite density, expelling all matter, energy, and space-time itself outward. In a certain sense, these two descriptions are saying the same thing. Cosmologist Lee Smolin proposed a hypothesis in the 1990s called cosmological natural selection. The interior of every black hole triggers a new Big Bang, creating a child universe. That child universe, seen from its parent universe, behaves like a white hole, expelling things outward while the parent universe sees nothing. Under Smolin's logic, the universe we live in is the interior of a black hole in some parent universe. Our Big Bang is the white hole eruption that parent universe would observe from outside. This is not mainstream, but it has not been completely dismissed by the physics community either. There is a more direct mathematical connection. In general relativity, a black hole singularity and the Big Bang singularity are the same class of object, places where space-time curvature approaches infinity and all existing theories completely break down. If the Big Bang is a white hole, then where is the black hole end it is connected to? Outside our universe, or in our universe's future? Nobody knows. But this is at least a meaningful physics question, not just philosophical speculation. Loop quantum gravity is one of the two main candidate frameworks for quantum gravity, the other being string theory. Its core idea is that spacetime is not an infinitely divisible continuum but is composed of discrete minimum units. Area and volume both have minimum values, called the Planck area and the Planck volume. This discreteness produces an important effect at the black hole singularity. In classical general relativity, matter collapsing to a singularity reaches infinite density and the equations break down entirely. In loop quantum gravity, when matter collapses to the Planck density, approximately 5 times 10 to the 96th kilograms per cubic meter, the quantum pressure from discrete spacetime generates a repulsive effect that prevents further collapse. The logic is similar to electron degeneracy pressure preventing collapse in white dwarfs, but operating at the level of quantum gravity. This repulsive effect would theoretically rebound the collapse into expansion. Matter reaching Planck density bounces back and begins expanding outward, which from outside looks like a white hole eruption. In 2023, Rovelli, Bausalt, and collaborators published more precise calculations giving theoretical predictions for the timescale of black hole to white hole transformation and the corresponding observable signatures. The results showed that if primordial black holes had masses between 10 to the 11th and 10 to the 15th kilograms, their quantum bounce completion time would fall approximately around the current age of the universe. If primordial black holes really did form in large numbers in the early universe, there may genuinely be white holes being born right now. The white hole concept has traveled a strange road. When it was mathematically discovered in the 1960s, it was treated as an interesting but physically meaningless byproduct. Nobody took it seriously. Then Hawking radiation appeared, the black hole information paradox started causing headaches, and white holes began to be treated as a serious option. Then the quantum gravity framework developed and white holes became a possible inevitable endpoint in a black hole's life. This trajectory is not appearing for the first time in the history of physics. The negative energy solution in the Dirac equation was considered mathematical noise that should be thrown out. It turned out to be antimatter. It was real. Schwarzschild's solution contained black holes, and Einstein himself believed they could not be physically realized. He wrote a specific paper in 1939 attempting to prove black holes would never form. Black holes turned out to be real, common enough that LIGO started capturing their collision signals. White holes now stand in this position, completely valid mathematically, unable to survive in classical physics, possibly real within the quantum gravity framework. Are we watching the same play performed again? This question has no answer yet, but it is precisely what makes white holes worth continuing to take seriously. There is one more uncomfortable question. If black holes really do eventually transform into white holes, what happened to the arrow of time? Black hole formation follows the second law of